Welcome class to this video on partial variation. In this video I will use 3 examples of partial variation to introduce the concept and illustrate its key features. We will then compare the characteristics of partial variation with those of direct variation. Lastly, we will do some application problems to hopefully reinforce your understanding of the concept. In our first scenario, we will describe a situation in which Mr. O'Connor is attempting to save some money. In our scenario, it says Mr. O'Connor had $40 in his bank account when he began saving $20 per week. You can see on the left the $40 that Mr. O'Connor began within his bank account. And so, because he starts with $40 before he begins tracking his savings, you could say that at 0 weeks, he had $40, as you can see in the table of values in the middle of the screen. We're also going to be showing this data on the graph on your right. And so if you look there, you will now see a point 0, 40 on the graph. Now we're going to track his savings week by week. You can see at 1 week he has $60, 2 $80, 3 weeks $100, 4 weeks $120, 5 weeks $140, 6 weeks, and he has $160 after 6 weeks. That data has been now put in a table of values and then plotted over here on the graph. And you should see that these two match each other exactly. Just to illustrate with 1 point, at 5 weeks $140, here on the graph we could find 5 weeks, and here it is $140. Now that we have a graph, let's determine the rate of change of the graph. We're also going to look at this question, what does it mean? What does the rate of change mean in this situation? We should have noticed in the last video that rate of change has a different meaning depending on the kind of graph you're doing. So for example, in a distance time graph, rate of change refers to speed. Or in a graph comparing time to the number of candies eaten, then the rate of change represents how many candies are eaten per unit of time. Lastly, in the graph which we did, which focused on the number of drawings sold and the money earned, then the rate of change in that case represented how much money is earned per drawing. What about in this situation? Well, first let's find the rate of change, and then we can discuss what it means in this context. So if you recall, to find the rate of change, we identify 2 points, any 2 points along the line. So in this case, we're going to use 280 and 6 160. We then draw a right angle triangle connecting the 2 points. The rise is the line going upward, and the run is the line going to the right. We can see that the rise was 80 and the run was 4. How did we get 80? We did 160 subtract 80. So here we were at 80, we went to 160. The difference between 160 and 80 is 80. And then how did we get 4? We did 6 subtract 2 and we get 4. So our rise is 80, our run is 4. We now use the formula rise over run, and we get 80 over 4. And that gives us the rate of change of 20. But what does it mean in this context? In this context, 20 means $20 in savings per week. Now recall, when we find rate of change, we're going to be describing it as slope, and oddly enough, we're going to be using the letter m for slope. So in this case, m is equal to 20. Now let's look at the definition of partial variation and see if we can use our scenario to try and make it a little bit more clear. The definition of partial variation is that partial variation is a relationship in which y varies partially with the value of x. The dependent variable is the sum of a constant, that is not 0, and a constant multiple of the independent variable. When we write partial variation as an equation, it is written in the form y equals mx plus b. That should look very familiar, it should look very much like direct variation to you, but you should notice there is an added element, the plus b. So let's review all the key elements of this equation. The first one is the dependent variable, y. The next one is rate of change, also called the slope, also sometimes called the constant of variation, m. Then we have x, which is our independent variable. And then lastly, this new part, which is called the initial value, also called the y-intercept when we see it on the graph. Let me try and connect now the second sentence in our definition, the dependent variable is the sum of constant not zero and a constant multiple of the independent variable, with y equals mx plus b. Let's look. The dependent variable, here is y, is, that's the equal symbol here, is equal to the sum. The sum means the result of addition, so you can see that here with the addition sign here. So y, the dependent variable, is equal to the sum of a constant that is not zero. That constant that is not zero is b, okay? Of a constant that is not zero plus the multiple, here's that multiplication, of the independent variable, a constant multiple of the independent variable. So here's our independent variable, and it's going to be multiplied by a constant multiple, which would be, in every case, the slope or the rate of change in the equation. If you didn't quite catch it, just do a quick rewind and listen to that again so you can see all the parts. The dependent variable is the sum of a constant, that's b, and a constant multiple of the independent variable. Let's now see how our scenario relates to the definition of partial variation by writing our scenario as an equation in the form y equals mx plus b. So remember, y is the dependent variable. In our scenario, what is the dependent variable? Well, the balance is the dependent variable. Its amount, its quantity, depends on the number of weeks that passes. Now it's going to be important to note that it partially varies, that the balance partially varies with the weeks. And we'll see what that means hopefully in just one moment. But for now, we know that the balance is the dependent variable. So the first variable of our equation in the form y equals mx plus b is going to be b. We now need to find the rate of change, and we discovered the rate of change in the previous screen is 20, and so we could have b is equal to 20. What's our independent variable? Our independent variable is the number of weeks. And so we could either use the variable t or we could use the variable w for weeks. Now, imagine if we stopped right here. Would we have the equation for this scenario? No, we wouldn't. If we use this equation, for example, if we used for 1 week, we would get that after 1 week, the balance was 20. Now, if after 1 week the balance was 20, and after 2 it was 40, and after 3 it was 60, then that would be direct variation, as y would vary directly with x, b would vary directly with w. However, this is partial variation, and if I multiply 20 by 1, that will not be enough in order to find his actual balance after 1 week. What would I need to do to 20 in order to get to 60? Hopefully you could see that I would need to add this 40, and therefore the rest of the equation is plus 40. 40 is the constant that is not zero that needs to be added to a constant multiple, 20, multiplied by the independent variable w, in order to find the dependent variable b. Alright, let's look at an example of that. If I substitute in 0 for w, what value will I get for the balance? You should see that I would get 20 times 0 is 0, so 0 plus 40 equals to 40, because at 0 weeks, the balance is $40. You can see that in the table of values here, and you can see that on the graph here. 0, 40 is a point on the graph. Let's now try and use the equation to predict how much money Mr. O'Connor would have in his bank account, his balance, after 7 weeks. So if we had the equation b equals 20w plus 40, which variable represents the number of weeks? That's right, it's w. So I could simply replace W with 7 in order to find out how much money he will have in his bank account after 7 weeks. Let's see that. I get 20 times 7 plus 40. 20 times 7 gives me 140, so I get 140 plus 40. And that gives me the value 180, which means there's a point 180 on the graph. And you can see it right there on the graph. So you can see how the equation is a very powerful tool, because now, using this equation, I could find out how much money Mr. O'Connor will have after 2,000 weeks, for example, if he's able to save that long, of course. But you can see I can use this equation to find out how much money he will have after any number of weeks, even half weeks. If I put in 5.5, for example, I would find the corresponding point on the graph. I would find the corresponding value for his balance after 5.5 weeks, for example. Let's now look at another scenario, which is oftentimes far more likely, where Mr. O'Connor is spending the money in his bank account rather than saving. You can see here that when Mr. O'Connor begins to spend his money, he has a balance, the current amount in his bank account, of $120. And you can see that represented by the 6 $20 bills that are there. If you look at the table of values, you can see that at 0 weeks, he has a balance of $120. And if you look on the graph, you can also see here represented the same idea, 0 weeks and $120 in his account. Now, when we do or track the weeks that he's spending his money, we're in fact going to go by 2 weeks as opposed to 1 week. And so think about it, in 2 weeks, how much will he spend? If he withdraws $10 a week, then in 2 weeks he will withdraw $20. And so as each set of 2 weeks passes, you will see the balance will go down by $20. And this will also be reflected in the graph over here on your right. So you can see 2 weeks he has 100, 4 weeks he has 80, 6 weeks he has 60, 8 weeks he has 40, 10 weeks he has $20 left, and at 12 weeks he's broke. He has $0 in his bank account. We would draw the line to represent the equation, the relationship between time and the balance. Now we're going to find the rate of change and discuss what it means in this context. But instead of using the graph, this time we're going to use the table of values. To find the rate of change using the table of values, you have to look at what's the pattern in the x column. So if we look here, what's the pattern? Well, each time it's going up by 2. Now we have to look at what are the first differences, and we've learned this concept before, in the y column. If we do the first differences over here, we find that the first differences are -20. Negative because his balance is going down. Before I show you how we can use now those numbers from the tables of values to find the rate of change, I'm just going to show you the method you're familiar with of using the graph to find the rate of change. Remember, I find any 2 points along the line. I then draw a right angle triangle between them. And the line going downwards is our rise. In this case, it's -40. And our line going to the right is 4. That's our run. Let's do it from another point on the line and another set of points. And here we have the rise of -20 and the run of 2. And you can now see, hopefully, the connection between what I did with the rate of change here on the graph with the rate of change that I found in the table of values. Here, the rise is -20. Here, the run is 2. -20 over 2. That's also going to be the same as what you can see here, -40 over 4. Because those are equivalent fractions. -20 over 2 and -40 over 4 are both going to give you -10. What does it mean in this situation? Well, in this situation, it means that $10 was withdrawn each week. Now let's use this scenario to illustrate, again, our definition of partial variation. Remember, y is the dependent variable, m is the rate of change or slope, x is the independent variable, and b is the initial value. In this situation, what is my dependent variable? Again, my dependent variable is the balance. So I could write B. Now, what is my rate of change, or the slope? My rate of change, the slope, is -10, as we discovered in the previous screen. What about my independent variable? In this case, it's the number of weeks. And then lastly, what is my initial value, the y-intercept? Well, if I have a table of values, I can identify the initial value by looking for where x is equal to 0. So you see weeks is the x column, and here x is equal to 0. Where x is equal to 0, the y value will tell you your initial value, or what is called your y-intercept. So ours is going to be 120. We could also find the y-intercept by looking at the graph, because the y-intercept is where the line connects with the y-axis, and it connects here at 120. Therefore, our equation is b equals -10w plus 120. One thing I've tried to communicate in this video and the previous video is that if I substitute a value for the independent variable, in this case w, I will always find the corresponding value for the dependent variable, in this case b. And this will be a point that is reflected on the graph over here. So to illustrate this, first I'm going to use the value 0 for w. So I put in 0 for w. What value will I get for b? And you'll see -10 times 0 gives me 0 plus 120 equals to 120. That means there's a point on the graph, 0, 120, where 0 is w and b is 120, and that's the point we just identified as the y-intercept. Let's try it with a different value. If you look here on the graph, you can see I plotted the points 0, 120, then we did 2, 100, 4, 80, 6, 60. But we have values that are missing in between here. We could use the equation to determine what those values are if we couldn't do so by easily looking at the graph. So let's try, for example, the value of 5 for w. If I substitute the value for 5 for w, I get -10 times 5 plus 120. -10 times 5 gives me -50 plus 120, and that gives me 70, which means there's going to be a point on the graph, 570, which you can see I just plotted, is right there. Before we move on from this example, I just want to try and tie it back into the definition. If you recall, partial variation is a relationship in which y varies partially with the value of x. So it does mean that y, in this case b, the balance, is going to change when x changes, in this case weeks. And it's going to change in this case by -10 each time. It's going to go down by 10 each time. It does change. There is a relationship. As weeks change, the balance will change. However, it's not enough to simply multiply the constant of variation -10 by the independent variable w. Because if you did that, you wouldn't have the correct balance. For example, if I did -10 times 1, then I would get -10. Was that my balance after 1 week? No, I would have to now add 120 to that number. So -10 times 1 gave me -10, plus 120 gives me 110. And we can see from the graph that that would be the balance after one week. Looking at the second part of the definition, it says the dependent variable is the sum of a constant, not 0, and a constant multiple of the independent variable. So again, I have my dependent variable. It is equal to the constant multiple, which is -10, times the independent variable, plus, the plus is that part here where it says sum, plus 120. Hopefully that's making the definition a little bit clearer for you. We're going to do one last example to hopefully cement this idea for you. Alright, last example. In this example, James is throwing a party. He paid $150 for the party room, the DJ, and the food. It's quite a deal. He is charging people $25 for a ticket to his party. Alright, so now what I want you to notice is if you look on the left-hand side, you can see that we have his expenses. This is the money that he spent. He no longer has this money. If you're thinking about the profits that he could make from throwing this party, at this point, when he sold 0 tickets, he is actually down $150. Those are his expenses that he had to pay to throw the party. We can see that on the graph, that on the table of values, then where we have 0 for tickets sold, the profits earned is negative 150. He hasn't earned any profit. He has some debt that he's going to try to recuperate by selling his tickets. And if you look here on the graph, we can then see the point 0, negative 150. Now we can see what will happen. This time the tickets are not going to go up by 1. I'm going to use intervals of 3. So let's see what happens. When he sells 3 tickets, remember each ticket is $25, he will have earned $75, and now his debt, his profits will only be negative $75, or he'll owe $75. So you can see that in our table of values here. You can see that in the expenses over here. He has $75 he still needs to try to recuperate. And you can see it over here in the graph where it says 3 tickets and he's at negative 75. Let's take a look what happens when he sells 6 tickets. When he sells 6 tickets, he has 0 profits earned. He's made back the money that he spent to throw the party. And so we can see here 6 tickets sold, $0 in profit. And we can see that here, 6-0 on the graph. He has sold 6 tickets and he has 0 profit because he had to cover the money that he used for the party room, the DJ, and the food. What about when he sells 9 tickets? Well, now he's got into the positives and he's now earned $75 in profits. 12 tickets, $150 in profits. 15 tickets, $225 in profits. 18 tickets, and he's now got $300 in profits. You can see if he can get quite a few people to come to his party, he's going to make a nice amount of money. So now we've plotted our points. If we did this in a real graph, we would then draw a line through our points. And now you know the next question. What's the rate of change? Let's find the rate of change, and we're going to use the table of values to do that. So remember, we look for the pattern on the left-hand side, and we find in this case that the pattern is it's going up by 3. And then we find the first differences on the right-hand side in the Y column, and we see that it's going up by 75. So if I wanted to do the rate of change or find the rate of change, I would do the rise. Remember, the rise is going to be the change in Y, so 75, over the run, which is a change of 3. So 75 divided by 3, and we get our rate of change is 25. And what does it mean in this circumstance? It means $25 per ticket. Remember, we use the letter M for rate of change or slope, and so M is equal to 25. Let's now try to make an equation for the scenario that we just described where James is throwing a party. What is our dependent variable? Our dependent variable is our profits earned. And so we could use the letter P for profits. P is equal to, what's our rate of change, our slope? It's 25 for $25 per ticket. And then our independent variable is the number of tickets sold, so we could use T. What about our initial value? Well, how much did James have to pay to start? He had to pay 150. Now, if you think about 150 and this 150 in terms of his profits, is this positive 150 or negative 150? Well, we know it's negative 150 because it's not the profits that he gets to take home with him. It's money he had to spend, and he's going to have to recuperate that money by selling more tickets. So it's in fact negative 150. So we're going to put plus negative 150. However, we never have to write two symbols, plus and negative. Adding a negative is simply subtracting, and so I can write it like this. P is equal to 25t minus 150. Now I could have seen that initial value also from the table of values here, where tickets were 0, the initial value was negative 150, and I could have seen it by looking at the y-intercept in the graph. When the tickets were 0, the profits was negative 150 in the graph as well. Now that we have the equation, we can use this equation to determine how much profits James would earn for various number of tickets sold. So let's take, for example, if he sold 90 tickets. If he sold 90 tickets, we simply substitute 90 for T. We would then do the multiplication. We're doing the constant multiple times the independent variable. In this case, constant multiple is 25. 90 is the independent variable, and it's 90. 25 times 90, I get 2,250. Now, that's not the answer in and of itself, because remember, we have to always combine it with the constant that we have, the initial value. In this case, that means we have to subtract 150, and we get $2,100. And that means that there would be a point on our graph which would be 90, 2,100. Now, of course, we can't show it on this graph here because the graph isn't big enough. But that's one of the benefits of the equation, is that I can substitute any value for t, and I can find the corresponding value for y, which it would be very hard to graph, because you wouldn't want to do a graph that had 90 values on the x-axis and 2,100 in the profits. That would be a rather large graph. The equation can save you a whole bunch of time. So what do the three graphs that we've looked at have in common? Well, the first thing you should notice is that the lines in all three graphs are straight because the rates of change are constant. Partial variation is a linear equation, so the lines are always straight, and you should know and understand by this point what it means to say that the rates of change are constant. They go up, the values of y go up by the same amount for x each time. The other thing you can notice is that the lines in all three graphs do not go through the origin 0, 0. That's an important characteristic of partial variation. So what are the differences in the graphs that we looked at in the direct variation video and the partial variation video? You should notice that the lines on graphs representing direct variation go through the origin. You can see the origin here and here, whereas the lines on graphs representing partial variation do not go through the origin, as we just said. What do the three tables of values that we saw in this video, which reflect partial variation, have in common? The first thing we can notice is that the first differences are constant in all three tables of values. In the first table of values, the first differences are all 20. In the second, they're all negative 20. And in the third, they're all 75. The other thing we can notice is that in all three tables, when x is equal to 0, y does not equal 0. And you can see that at the top of each of the graphs. Now we can summarize our lesson before we move on to some application problems. The first thing we should remember is that partial variation is a relationship in which y varies partially with the value of x. The dependent variable is the sum of a constant and a constant multiple of the independent variable. Now that constant can't be 0, b can't be 0. If it is 0, then it would just be direct variation. We also learned that as an equation, partial variation is in the form y equals mx plus b, where y is the dependent variable, m is the rate of change or slope, x is the independent variable, and b, very importantly, is our initial value or our y-intercept. With regards to graphs, the line representing a partial variation does not go through the origin, does not go through the point 0, 0. And those examples you can see on the screen, those are all examples, those lines of partial variation, because none of those lines go through the origin. With regards to tables, a table of values representing a partial variation, the first differences are constant, and if the table has a row with the value x equals 0, then y will not equal 0 in that same row. And you can see a couple of examples that we just saw from earlier there as well. Here you can see a chart summarizing the differences between direct variation and partial variation. Direct variation is in the form y equals mx. Partial variation is in the form y equals mx plus b. Direct variation has a graph where the line goes through the origin, whereas in partial variation, the lines do not go through the origin. In tables of values, when x equals 0, y will equal 0 for direct variation, and for partial variation in tables of values, when x equals 0, y will not be equal to 0. Now we can apply what we know to answer some application questions. What are the y-intercepts of these graphs? Pause the video here and answer the question. The answer for the first graph is 4, because we can see that the line intersects with the y-axis at the number 4. The y value where the line intersects with the y-axis is 4, therefore the y-intercept is 4. And for the second graph, The answer is 20, because again, the line is intersecting with the y-axis where the value is 20. I know this value is 20 because two spaces make 40, and therefore each space is worth 20. This we can know is 20. That is the y-intercept in this graph. The next question is, which of the following situation describes a partial variation? Anthony earns $20 plus 50 cents for each bag of peanuts that he sells. Julie ate 4 candies per hour. Maria started reading a book and read 20 pages per hour. To rent a canoe, it costs $15 per hour. Pause the video and answer the question. The answer is Anthony earns $20 plus 50 cents for each bag of peanuts that he sells. In this example, the rate of change is 50 cents. Each time he sells a bag of peanuts, his earnings will go up by 50 cents. But there is an initial value of $20. Therefore, this is partial variation. The next question is, a gym membership costs $50 plus $2 for each visit. Which of the following equations represents the relationship between the number of visits and the cost? Is it C equals 2n plus 50? Is it C equals 50n plus 2? Is it C equals 2n? Is it n equals 2c plus 50? Pause the video and try to answer the question. The answer to the question is C equals 2n plus 50. That's because for each visit it's $2, so 2 times the number of visits, but then you have to add the $50 for the membership cost. So C equals 2n plus 50. Looking at the next question, it says which of the tables below reflects a partial variation? Pause the video and try to answer the question. The correct answer is the first graph. In the first graph, you can see that the rate of change is constant. The first differences are all the same, 3, 3, 3, 3, and when x is equal to 0, y is not equal to 0. That is not true of any of the other graphs. In all the other graphs, when x is equal to 0, y is equal to 0. And some of the graphs, or one of the graphs, doesn't even have a constant rate of change. So the answer is this first one, because when x equals 0, y equals something other than 0, and the first differences are the same. Looking at the next question, it says which graphs represent partial variation? Pause the video and try to answer the question. The correct answer is the first, the third, and the fourth. In all 3 of those graphs, the line does not go through the origin, therefore they represent partial variation. Last question. Gavin's Cafe offers a VIP membership deal. You can buy a coffee card for $5 and then pay 50 cents per coffee. The equation for relating the number of coffees to cost is C equals 0.5n plus 5. If someone purchases 9 coffees with the VIP membership deal, how much will it cost? Try to pause the video and maybe use a pencil and paper to try and answer this question. The answer to this question is $9.50. You get this answer by substituting in 9 for n and multiplying 0.5 by 9, and you will get $4.50. Then you have to add the cost of the VIP membership deal, and you will get $9.50. That brings us to the end of our video. Here, just food for thought. Now that you understand direct and partial variation, do you understand the video thumbnails of these 2 videos that you've just watched?